Welcome and thank you all for finding time and attending today's webinar, Frontiers in Catalysis and Design, Frontiers in Catalysis Design for Sustainable Technologies. My name is Jeff Kenvin and I am the Technical Director of Micromeritics Instrument Corporation, a global leader in material characterization technology. I'll be your moderator for today. Today we have a guest speaker, Professor Javier Pérez-Ramírez from ETH Zürich, where he is the Chair of Catalysis Engineering. If you have any questions, please write them to the chat during the Q&A session following the webinar. The webinar recording will be available on our landing page, micromeritics.com/webinar, in the next 5 to 10 days. You'll also be provided a link to the recorded webinar via email once it becomes available. I am pleased to introduce today's speaker, Professor Javier Pérez-Ramírez. After Javier received his PhD, he started his career in corporate research before pursuing a career in academic research, first at the Institute of Chemical Research of Catalonia, before moving to his current position at ETH Zürich, where he has created the Advanced Catalysis Engineering Group that focuses on the design of heterogeneous catalysts and research and reactor concepts devoted to sustainable technologies. Javier is currently the editor-in-chief of the journal Catalysis Science and Engineering. I'm pleased to hand over to Javier now to learn more about Frontiers in Catalysis Design for Sustainable Technologies.
Well, thank you, Jeff, and good afternoon or morning to everyone. I hope you are doing well, and I would like to start by expressing my gratitude to Micromeritics for the honor of being with you today. And during the course of this webinar, I'm going to share with you recent highlights of my group rooted on catalyst design that address current energy, resource, and environmental challenges. Let me first take a step backwards and set the scene. Except for the pandemic that we are living today, we are enjoying the highest quality of life that society has ever achieved. And this stems from our ability to make a plethora of products ranging from fuels and bulk chemicals to polymers, pharmaceuticals, and many other consumer goods. 90% of these chemical transformations require catalytic systems. And so going from the root of the tree to the tips of the leaf. And new catalytic technologies will be really instrumental in order to tackle the transition from fossil to renewable resources, as well as to improve the utilization by minimizing waste. This need of improved catalytic technologies is exacerbated by the well-known global trends, including the stark anticipated increases in population, life expectancy, and energy demands. The birth of industrial catalysis was strongly linked to societal progress. This is a picture of an early chemical site at Widnes in the UK, England, around 1850. While this image has a symbol of prosperity, there is another P associated with this image, and that's pollution. And you can see the smoke from the chimneys that actually contain hydrochloric acid, among other toxic compounds. This hydrochloric acid was the byproduct of the Leblanc process to make sodium carbonates, and pioneers like Deacon and Hurter implemented copper chloride catalyst to valorize this waste into chlorine, which was then marketed as bleaching powder. Ultimately, the catalyst actually that was implemented was unsuccessful due to stability issues dealing with copper chloride volatilization and the reaction conditions. And this outcome is understandable. That means this lack of optimality, because implementation occurred with a strong lack of understanding, and that actually has been a repeated feature through the history of our field of our catalysis. Very often technology developed prior to science. We are now in a different position due to the extensive range of tools, synthetic, analytical, theoretical, digital, that enable us to design catalytic processes. And one of these examples I want to start with is the development of active and stable catalysts for chlorine recovery, exactly the decon application, which remained unsolved for over 140 years and became a pressing need around year 2000 for recycling this halogen in the manufacture of polyurethanes and polycarbonates. Well, the multi-scale nature of the catalytic process is shown here in connection with this application of chlorine recycling. It highlights that we go from kilometric plants to nanometric atoms and molecules. So you can see that hydrochloric acid oxidation occurs in a cascade of adiabatic reactors hosting the catalytic material. This gives you an impression of the support and the active phase and the binder actually. And if you go deeper into the atomic scale, what you see is the reaction mechanism, the engineering that starts at the atom, where oxygen cleaves, hydrochloric acid cleaves, forming OH groups, forming water and forming chlorine. This is actually the state-of-the-art catalyst for hydrochloric acid oxidation, and this became a breakthrough upon discovery in early 2000 and optimization and implementation at the end of last decade. And the catalyst is actually what you see in the picture is 2 layers of ruthenium oxide epitaxially grown on tin dioxide. This is the first example of a catalyst design that was unprecedented a couple of decades ago. Now what you see here is 2 layers of ruthenium oxide and not 3, and 2 and not 1. So it's very important to have 2 in order to optimize cost. 3 is underutilization of metal. 1 will have a very strong interaction with the tin dioxide support, so the activity of the catalyst in chlorine evolution will be insufficient. Tools like we show over here on the right, aberration corrected microscopy, enable us by zooming to see that actually in the industrial catalyst we have 2 layers of ruthenium oxide epitaxially growth on tin dioxide, and the same active phase, ruthenium oxide, supported on alumina or silica, displaying nanoparticles rather than films, will be as mediocre as the copper chloride catalyst developed by Decon. So that is an example of how important the nanostructure of a catalyst is. If we go to another long-standing example of a very successful catalyst, that's the Lindlar catalyst for stereo and chemoselective hydrogenation of alkynes. So very complex molecules, and you want to hydrogenate a triple bond into a double bond. And the prototypical catalyst is a palladium lead catalyst. So the palladium catalyst is heavily poisoned by lead and also by quinoline in order to make it selective. There was a strong push, and still a strong push, to certainly reduce the amount of noble metal, but most importantly, to get lead out of this catalyst formulation because of environmental reasons. So that led us to the need to understand what the Lindlar catalyst looks like and why it's so selective when it's so heavily poisoned. Those studies ended up in this very beautiful picture that shows that actually when you alloy palladium with lead and additionally you absorb quinoline on the surface, you form these trimeric ensembles which are very selective because they are enough to activate hydrogen and to proceed with the hydrogenation, but not so active in promoting hydride formation, which will actually decrease the selectivity. So you will actually end up hydrogenating the triple bond towards the single bond. Now, with this understanding of very well-defined motifs, in this case a trimeric ensemble of palladium, the design of better catalysts, that means containing much less palladium and containing no lead, could be undertaken. And it's all based on replicating this motif, this trimeric ensemble motif, in more environmentally friendly catalysts. So that's our descriptor, the ensemble size and the ensemble geometry. And with that, we were able to go from the Lindlar catalyst with a certainly reduced activity containing a lot of palladium to systems that contain 1 order of magnitude less palladium and that they are environmentally friendly. And these systems are characterized by the fact that they contain the same type of ensembles, trimeric ensembles of palladium, as you had in the Lindlar catalyst facilitated by lead. In this case, it's facilitated by having a crystalline palladium sulfide surface. In this case, it's facilitated by doping of the palladium crystal with boron, which sits at specific positions of the lattice, leading to these trimeric ensembles. All facilitated by the very good understanding of the Lindlar catalyst in order to proceed with a more sustainable system. But it's not only crystalline structures that could be developed. In catalysis, many other design approaches can be used. So I think this is another very beautiful example, comparing a naked nanoparticle with a ligand modified nanoparticle for the production of hydrogen peroxide by direct oxidation of hydrogen. If you don't have the ligand, the selectivity to the peroxide is very low. You're gonna form mostly water. And in contrast, when the ligand is covalently bonded to the palladium surface, the selectivity to hydrogen peroxide increases to 80%. And this is due to the fact that the steric interactions between this ligand and the density of the ligand on the surface of the nanoparticle made that some of the intermediates, instead of lying horizontal on the surface, lie vertically. And the vertical orientation of the OOH intermediate in hydrogen peroxide synthesis leads to high selectivity to hydrogen peroxide because the oxygen-oxygen bond leading to water, the undesired product, is not cleaved. So that's how you can also use nanostructuring to design new catalysts and new reactivities. And that's another beautiful example of how a nanoparticle of palladium that is very unstable in acetylene hydrochlorination because of redispersion effects can be made much more stable by an order of magnitude by attaching a graphene layer on the surface, just one layer of graphene, one atom of carbon on the surface of the graphene, which kind of embeds the ruthenium nanoparticle and decreases the kinetics of dissolution of the redispersion, of the nanoparticle. So these are a few examples of creative catalyst design by looking at the nanostructure at the atomic level. And so I have an example here that deals with metal utilization, in particular noble metal utilization, because it's also a trend and it's a very hot topic to go from nanoparticles to single atoms. And single atoms are the maximum expression of dispersion, but single atoms also offer other kind of advantages, as you will see in a minute. If you look at single atoms, always the critical thing is how stable these single atoms are under reaction conditions. So you want to avoid any sintering during reaction conditions. And for that, it's very important to design the right host. So our work has very much focused in the beginning of carbon nitrides, which contain these six-fold nitrogen coordination sites, which are able to stabilize single atoms. In the picture that you see here is palladium. And by electronic donation between the nitrogen and the metal, this metal gets heavily stabilized in the structure. You can see that actually, if you look at this time resolved micrograph, where the single atom is mapped in the cavity of the nitrogen of the carbon nitride, and then you see the very important stability. Of course, if you see this movement, you see some movement is not because the atom is moving, it's because the grid of the microscope is moving. So this atom is really in place. And the fact that there is this very strong interaction between palladium and the host, the nitrogen in the host, leads to the fact that palladium is highly charged. So you have cationic species rather than metallic species. And this opens really very nice opportunities to utilize these systems in replacing homogeneous catalyst because actually the solid, the host, acts as a ligand to the palladium atom, which is charged, resembling a lot the structure of this 3-phosphine that is used in classically in many different applications in homogeneous catalysis. So this single atom catalysis, catalyst, heterogeneous catalyst, is in between a homogeneous metal complex and a nanoparticulate catalyst. And so that enables us to exploit chemistries that go in the direction of replacing homogeneous catalyst by heterogeneous single atom catalyst, which certainly lead to sustainability in the sense of improving catalyst separation in pharmaceutical applications or fine chemical applications. Here's an example of the flow Suzuki coupling, a classical reaction to produce biphenyls used extensively in industry, where we have compared the single atom catalyst with the state-of-the-art commercially used triphosphine homogeneous system, and we are able to get much higher turnover frequencies and much more stability. That's the most important thing, due to the characteristics of the system. To explain the high activity and stability of this system towards leaching or towards agglomeration, I think this picture will enable us some clarity. This is the 583 is the coordination of the atom to the host, right? So it's surrounded by 6 nitrogens, about 6 nitrogens. When there is the adsorption of the bromobenzene, of course, the single atom loses some coordination to the host because it's coordinating the reactant. So it decreases to 2.76, as you see over here. The reaction proceeds, and the beauty of this system is that the single atom can adapt its coordination in this cavity. So it's actually locked enough not to leach, but is flexible enough to adapt its coordination optimally to the adsorption of reactants or intermediates, leading to a decreased energy transition and therefore a very high activity. Now you see at the minute the biphenyl group is going to be formed, and the palladium atom is going to recover its original coordination to the host of around 6. So this adaptive coordination concept is very important, and actually this system mimics, I repeat, the beneficial function of the ligands in metal complexes, but in an extended scaffold, highlighting the technological potential for the heterogenization of challenging processes, making the manufacture of fine chemicals and pharmaceuticals more sustainable. The carbon nitride host is also able actually to stabilize higher nuclearity species. As you can see here, dimers and trimers of palladium. And this has been achieved by depositing metal precursors with the desired nuclearity. And so you can see here some molecular dynamics that shows actually how these species, the dimers and the trimers, are accommodated in the cavity. And what these studies allow is a platform to derive structure performance relationships with atomic resolution. So you are building clusters with the optimal size, because it's not always the single atom is the best system. It depends on the demands on the reaction. But going from one atom to 10,000 atoms in a nanoparticle, it's a very extreme situation, and therefore this approach enable you or us to derive what is the optimal nuclearity of a metal system for a given reaction, thereby leading to improved metal utilization. Okay, this is another example that I want to share with you. It's a recent example, and this is the acetylene hydrochlorination, where single atoms have been found recently to be promising systems, and these single atoms are meant to replace mercuric chloride. Mercury is the catalyst. Mercuric chloride is the catalyst for hydrochlorinating acetylene to produce the vinyl chloride monomer, which contributes to 30% of the world PVC capacity. This application uses 1,200 tons of mercury per year, and it generates 600 tons of mercury waste and 40 tons of mercury emitted in the air per year. So you can imagine that at the Minamata conversion of mercury, this application was regarded as a very important one to have a replacement by more sustainable systems. And so we very recently studied, you can see here, noble metal catalyst based on single atoms in order to attempt this transition. It is well known from the work of Hutchins that gold, and gold single atoms in particular, are excellent materials. What you can see here is a gold single atom attached, coordinated to an oxygen group of carbon, and what you see on this on the left is the same gold coordinated to nitrogen, to a 3-pyridinic nitrogen side on nitrogen doped carbon. And what you see here is the energy of stabilization, 1.71 and 2.69 electron volt. So nitrogen helps binding the gold strongly. So this is gold chloride, gold 1 chloride. So it's a cationic species of gold with a chlorine ligand. What happens is actually this species is not it doesn't have a long lifetime in hydrochlorination, and this species doesn't have a long lifetime in hydrochlorination either. They are extremely active, but this one leads to sintering because it's too mobile on the surface, and this one leads to coking because the nitrogen defects heavily promote coking in acetylene hydrochlorination. So these are the two main deactivation mechanisms that happen, which make this technology of less value. So what we thought is, instead of dealing with gold, we took platinum. And we know platinum does not require any nitrogen ligand because it will stabilize already very strongly on an oxygen side. So that's a platinum single atom. So it's a platinum chloride. So it already stabilizes with minus 3.83, much stronger than even gold on nitrogen doped carbon. So we have the higher stability towards mobility with respect to the single gold on oxygen, but the advantage of not having nitrogen that could favor coking. So with this system, actually what you can get is a very stable behavior. This species doesn't come doesn't come out of the blue. And a speciation analysis was done in order to check the geometry and the environment of the single atom, and the palladium chloride, the platinum chloride that you see here attached to the oxygen defect in the carbon structure was found to be the most stable and the most active for the reaction. As a consequence, we are just looking at which star has the brightest light that leads to a maximum catalytic activity without compromising stability. And that's exactly what happens with platinum. Gold is extremely active in the beginning as single atom, as you can see here in red, but during time on stream, it heavily deactivates because it is mobile, and it sinters into these huge gold nanoparticles that are inactive. Now, platinum single atoms are less active because they are more attached to the host. However, because of its unique stability, already after 30 hours on a stream, they are superior to gold system. So this is a little bit trade-off between initial activity and the real key aspect, which is stability of a catalytic material. So I've shown you extensively to you that there are few and many strategies to break linear scale relationships in order to design sophisticated materials, still scalable, that can be applied for specific applications. So if you look at this perspective, it summarizes actually many of these material-related strategies, nanostructuring-related strategies to break these linear scale relationships in order to find unprecedented reactivities. For the rest of the talk, I'm going to focus on two molecules, and I'm going to focus on the activation of methane, and I'm going to show you some tools for understanding catalytic processes dealing with the direct functionalization of methane, and also some catalyst design aspects related to CO2. Let's start with methane. So, you know, flaring is a big issue. It wastes 3.5% of the world natural gas. This is something that represents in the order of 15 billion US dollars. And the point here is that valorizing methane in very remote locations is not economically attractive because the transport of this gas to, you know, mega plants for making syngas is prohibitive and cost ineffective. So our approach has been, okay, why don't we make plants on wheels that go directly to the source, to these remote sources of methane, in order to valorize it into liquids or valuable compounds on site, rather than transporting the gas to a mega syngas production facility. And one possibility that we have studied for years is the use of halogens to activate methane or other alkanes to produce, in the case of methane, methyl bromide as platform chemical to further couple it to produce olefin, oxygenates, aromatics, or other compounds. This technology, both in the in the coupling step, has the following issue, and also in the bromination step. Both in the bromination and the coupling step has one issue, and this is that hydrobromic acid is released. So in order for this process to be economical, all the bromine will need to be recovered back into the main bromine, and this can be done by HBr oxidation. So you oxidize HBr into bromine, so you have a closed loop of the halogen. And a second option will be to take this HBr waste and do the so-called oxybromination, where you react HBr with the alkane and oxygen on a catalytic material to produce methyl bromide again. So this will be even a more intensified way. This reaction is very challenging, and designing selective catalysts that do not lead to over-oxidation products or polybrominated products is actually was a subject of a study in our laboratory. And for studying this, we needed very sophisticated techniques in order to be able to design the catalytic materials. And I'm going to share with you some of these techniques. So I'm going to show you an example of a cartoon of the mechanism of a catalyzed methane oxybromination. So what the surface does is actually activating oxygen and HBr, and that will lead to water, molecular bromine and bromine radicals. And bromine radicals will react with methane in the gas phase to produce the methyl radical and HBr, and the methyl radical will react with bromine to produce methyl bromide. So this is a heterohomo reaction, actually, where the surface is making the bromine radicals or molecular bromine, and the attack of bromine or radicals to the methane is happening in the gas phase. How do we know that this is the mechanism? So this took some effort. So we need techniques to understand what's happening on the surface and what's happening on the gas phase. So to understand surface related aspects, we put our attention on prom gamma activation analysis, which would be a technique that enables to quantify the halogen coverage and the reaction conditions using a source of cold neutrons that will basically excite all the metals on the surface, including the chlorine adsorbates, and upon relaxation, they will just emit prom gamma rays. And these prom gamma rays have an energy that is characteristic of the element. So during reaction conditions of methane oxybromination, typically a high temperature reaction, we see the signal of the metal, which in this case was vanadium. So this is the surface of vanadium phosphate, but you see there is no bromine whatsoever, because at that temperature, all the bromine is already expelled into the gas phase. So for that to be proven, we will need to verify that we have bromine and methyl radicals in the gas phase. And for that, we need other technique that is actually sensitive to gas phase radicals. And this is PEPICO, photoelectron photoion coincidence spectroscopy, using vacuum ultraviolet light again to excite the gas phase species and to get the mass spectra to prove their absence or existence under reaction conditions. So this was done in operando mode, so at the same time as the reaction was happening under operating temperature conditions. And what we could see is that with this tool, we were able to indeed monitor methyl radicals in the gas phase and bromine radicals in the gas phase, as well as bromine, molecular bromine, what you see here in gray. So that verified our mechanism. So what we had to do in order to design catalysts with these two techniques is basically to compromise the activity of the surface of the catalyst so that it's able to oxidize HBr to produce bromine radicals or molecular bromine, but should be inert towards oxidation of the desired product. Otherwise, we will get carbon dioxides. That was the way we did it. So we start with a very low selectivity to the desired products. So this is in blue here. These are bromomethanes. Undesired is carbon dioxide. So we start with very low because ruthenium oxide is highly redox active. So it's going to oxidize HBr, but it's also going to oxidize methyl bromide into COX. And you see the evolution moderating the redox properties of the surfaces so that we reach optimal values with europium oxybromide or lanthanum vanadates, where only 2 or 3% of selectivity goes to carbon dioxide and about 97 or 98% goes to the desired products. So this is an example of using sophisticated techniques to drive catalyst design as well and catalyst development. So here the issue with this chemistry, with alkane functionalization using halogens, is how to study what happens on the surface with respect what happens in the gas phase. And with methane, we were not able to conduct the bromination of methane step on the surface because of the difficulty to activate methane on the solid. So it happened in the gas phase, and that's why we require high temperature. But if we go with other alkanes, like for example ethane, to produce to target ethylene, a different situation appears. What you see here is that if you do ethane oxybromination, ethane plus HBr plus oxygen, at a conversion level of ethane of 20%, you get a supermarket of products. You get ethylene, you get ethyl bromide, you get cracking, and you get COX. And the reason is that most of the chemistry is actually happening in the gas phase. And we see that because bromine is always appearing in PEPICO in the gas phase, while the coverage of bromine on this catalyst surface, in this case, it's an iron phosphate catalyst, is close to zero. So what we need to do with ethane is to bring all this chemistry down on the surface. And that you can do by using chlorine, because chlorine will absorb more strongly on the catalyst surface. And so what happens is that you can operate the reaction so that there is no radical formation in the gas phase. So this is ethane oxychlorination. You have a high coverage of a chlorine on the surface, and because you are confining all the reactivity on the catalyst surface, it's much easier to control the selectivity, to the point that by ethylene, by ethane oxychlorination, ethylene selectivities of 100% can be attained. So that really shows the effect of the halogen in determining where the chemistry is taking place. Left side, gas phase, bad. Right side, surface, good. And so what you see is that in oxychlorination, OC, on oxychlorination, these are the yields that one can derive. And so yields of up to 90% can be achieved. And so about 90% selectivity to ethylene at 100% ethane conversion. So it's an impressive value, exceeding other commercial technologies for producing olefins. So this is a very, I think, a very promising technology to produce olefins from natural gas components, C2 and as well as C3, which I'm not showing you, but we have done as well. All right, so the last example I want to show you, after showing you how these advanced tools help us bring in technologies forward, deals with carbon dioxide. So how to make the most out of carbon dioxide in order to minimize effects of CO2 into, for example, climate, or to think about using carbon dioxide as feedstock to make the materials that we are making today from oil, for example, or oil-derived platforms. And our attention originally focused on methanol. Before I show you some catalyst design aspects, I want to show you that a planetary analysis that we did, because when you develop the catalytic technology, certainly the atomic scale is extremely important, but also the process scale is reactor and process scale are important, supply chain is important, but at the end, the planetary scale is very important, and this is very much in the direction of sustainability. So we conducted what we called a plan-to-planet analysis with my colleague Gonzalo Guillén, a professor here at ETH on systems engineering, which is related to the different to the 9 or 8 planetary boundaries that should not be surpassed, and that's atmospheric CO2 concentration, energy imbalance. So these two are very much connected to global warming, freshwater consumption, land systems change, phosphorus flows, nitrogen flows, ocean acidification, and stratospheric ozone depletion. So if you take the way methanol is produced today, and that is from syngas coming from fossil fuels, actually we are exceeding the energy imbalance at top of atmosphere. That means this is an unsustainable way to produce methanol. Okay, and we are also exceeding nitrogen flows. In this analysis, in this LCA's analysis, at the end of the day, this is a life cycle analysis at the planetary level. It's important to deal with the share to the planetary boundary. And so the size of this blue region indicates how important that planetary boundary is to the overall assessment. So indeed, nitrogen flows, exceeding that is not so critical, because that planetary boundary has a little effect compared actually to the energy imbalance. So actually this is the problem in methanol synthesis from fossil fuels. And if you will go into CO2 hydrogenation as a way to produce methanol, taking wind as a renewable energy source to produce green hydrogen, what you see is indeed that the planetary boundaries of global warming are actually satisfied. And yes, indeed, you are shifting you are doing burden shifting to other planetary boundaries, like in this case, fresh water. However, this is again less relevant, because that planetary boundary hardly counts on the overall outcome. Okay, so this is to justify that indeed we are doing things in an unsustainable manner, and we have to look into alternatives. So our work on CO2 hydrogenation to methanol started with the discovery of indium oxide as catalyst for this reaction. And this catalyst is very special because it's highly selective to methanol, so it produces very little CO, as well as very stable. So this is a test over 1,000 hours on a stream. The design of this catalyst was attempted from the point of view that we were convinced from the very beginning that we needed reducible oxides where we could control the vacancy chemistry, so that we are able to create coordinatively unsaturated sites at selected places of the solid without leading to over-reduction of the surface, so that we can orchestrate the reaction in a selective manner. And indium oxide is a very good example because it's extremely anisotropic. So it has very different oxygens on its surface. Here you see different oxygens with different colors. And for example, these oxygens in purple have a much lower energy for being removed. That is to create a vacancy. With respect to the yellow, for example, oxygens in the lattice, which are extremely hard to remove, which actually leads to very difficult to reduce oxide under CO2 hydrogenation conditions. Because we can change those conditions of CO2 hydrogenation, we could produce a solid with a controlled vacancy chemistry, so that we are operating at a condition where only selected oxygen atoms from the surface of the catalyst are actually removed. The rest remain, and this forms again ensembles. In this case, it's a indium 305 ensemble with a vacancy where CO2 can activate and hydrogen can activate. So this shows you the DFT image was computed by my colleague Nuria Lopez at ICIQ of the reaction where you have hydrogen activation and CO2 activation, and then is the sequential addition of 3 moles of hydrogen to the CO2 molecule producing all series of intermediates until the gas phase methanol is produced. And this is the energy profile. The reason I put the energy profile here is twofold. First of all, I want to put it to show why this catalyst is selective to methanol and not to CO, which will be the reverse water gas shift. And that's because the reverse water gas shift reaction has a much higher energy intermediate, which leads to the system going the blue pathway, going to methanol. And the second reason why I put this is because although the material is extremely selective, one of the problems of using indium oxide as well as other oxides, like for example zinc oxide, is the very difficult activation of hydrogen on these systems, rendering them less active compared to copper-based systems. So how can we improve the activity of this system, keeping the unique selectivity pattern that we have towards methanol? So to that, we looked into doping effects. So contrary to professional sports, doping in catalysis is absolutely legal and allowed. So we doped indium oxide with a hydrogen splitting element. And obviously one of these could very well be palladium. So no surprise, palladium would be a good hydrogen splitter. And so our first effort was, okay, if we put palladium on top of indium oxide, then we're gonna have a good activity because we're splitting hydrogen, but hopefully the selectivity pattern is still determined by indium oxide. Well, luckily, this is the case in the beginning. So if this is the base activity of indium oxide, and you put palladium on indium oxide by dry impregnation, DI, still trying to form very dispersed species, because we know that if we form palladium nanoparticles, we are going to alter the selectivity patterns towards CO, because palladium nanoparticles are extremely good in catalyzing the reverse water gas shift. So we will violate our intention of keeping the selectivity pattern to methanol of indium oxide. Indeed, by doing that, very dispersed palladium species, atomically dispersed on the indium particles, we get a significant promotion of space-time yield, say a factor of 3 in this example. But what happens is that during reaction, the activity declines heavily, because these palladium atoms are quite mobile and they cluster into nanoparticles on time on stream. So if you analyze the catalyst after 75 hours, you started with almost a single atom of palladium, very well dispersed, and you end up with a pretty large palladium nanoparticle, which displays the reverse water gas shift, and that's why the methanol productivity starkly decreases. So here our analysis of the design has been, okay, we need to anchor as much as possible these isolated sites so that they don't sinter, and so we can keep the hydrogen splitting ability and the vacancy creation ability of the palladium, but keeping the selective behavior of indium oxide. To that end, we prepare the catalyst in different ways, and the one I'm showing you here is called CP. That's co-precipitation. By co-precipitation, playing deeply with this is not an afternoon job, by the way, playing deeply with the recipe, you could tailor the fraction of palladium that is in the lattice of the indium oxide with respect to the fraction of palladium that is on the surface of indium oxide. This can be tuned because some of the palladium is going to be basically substituting indium in the co-precipitation process. But upon saturation of the lattice by palladium, the remaining palladium will be actually on the surface of the catalyst, right? And we know this is buried on the subsurface, so it's not going to be active. But actually, this palladium lattice species has a very important role in the design of the catalyst. So that palladium pocket is the same as this palladium pocket. This is surface palladium site. Again, we have a very high activity initial, very similar to the dry impregnation. but the difference is that this catalyst is stable. This species is mobile, but this species is not. So what happens, and this is our assumption of looking no change in atomic dispersion, is that the that this atom, it should move actually exactly, there you go. It's actually anchored to this side, forming a dimer. And I don't know why it's moving so slowly. It should move faster to show you this dimer. Let me see it over here. Yes, so this is the sign. This is the dimer that you form. So this was the palladium in the lattice, and this is palladium in the pocket. So once palladium in the pocket meets palladium in the lattice, it actually forms a very stable palladium-palladium bond, which will not move the surface palladium atom anymore. And that's why, in contrast to the impregnated catalyst, we keep this atomic dispersion. What we have found, and this still is a result of DFT analysis, is how big can the cluster of palladium be so that we don't manifest the reverse water gas shift that you will have on a pure palladium system. And actually, this was done by studying activation energies for either methanol production or CO production on the different models. And what we found is that the border between selective behavior to methanol and unselective behavior to methanol or selective behavior to CO is 1 atom thick. So a dimer on the surface, which will be actually a trimer on the material, is still highly selective to methanol, but having a tetramer already leads to nanoparticle type behavior, leading to reverse water gas shift. So that is an example of how critical nuclearity effects in catalysis are. 1 atom too much, and then you are dead. That's how precise we have to be. And that's how precise our tools have to be. This process of making methanol from CO2 has been advertised in recent press releases by Total, where they intend to, and they are studying to bring this system into demonstration, large-scale demonstration. So here's a press release that we made last year with all this information. 100% recycled CO2, so 100% methanol recycled from CO2. So these are my concluding slides. So I hope I have shown you that catalyst design, it's not an easy task, but luckily we have tools, very different tools, to basically try to attempt what we are looking for. And that what we are looking for is based on descriptors. Ultimately, these descriptors come from a multi-sport activity. So catalysis is a multi-sport activity where many different disciplines and specializations are coming into play. And that's why really larger and larger teams are required in order to make significant contributions that move us forward rather than incrementally into new design aspects in catalysis. And to this end, I want to finish by introducing you a program that we are launching in Switzerland from August 1st. So it's 2 weeks from the start, which is called an NCCR. So that's a long-term National Center of Competence of Research. And so the Swiss government has decided that sustainable chemistry through catalysis, it's a strong point of the country where we have to invest on making carbon neutral chemicals in the country. So this is a national-wide program that will last up to 12 years. It's really long-term research that goes from the very small molecule activation to the creation of very complex drugs, and not only from fundamental aspects, but also from demonstration. I like to acknowledge many people that have contributed to the examples that I have shown you, and also many different organizations And finally, I'd like to thank my group, the Advanced Catalysis Engineering group at ETH. And here I show you a picture of it. And I'd like to thank you for your very kind attention. Thank you very much.
Thank you very much, Javier, for this wonderful webinar. I'd like to open up the chat window for any questions, and we already have a few. Javier, you presented many nice reaction studies during this presentation. What's a typical duration for this? Because I'm looking at the timescale for your work, and it's all the last few years, and there were many reaction studies. What's a typical time period for evaluating a new candidate?
So the examples I have shown you, they will typically require between 5 and 10 years of work. If you are asking me how long it took us to, for example, to come up with the indium oxide material, that was 5 years, and going into more scale-up aspects, going into more, technical application of this catalyst is going to take another 5 years. All the methane chemistry I have shown you with the development of these tools like prom gamma activation analysis and the photoelectron photoion emission spectroscopy. These are projects between 3 and 5 years to really gather information.
Once you have that candidate, how long then would you test it in a reactor?
Right. So yes. So this is a very important question. Since we are aware and very sensitive to the fact that stability is a critical parameter in any catalytic technology, so we don't want to have metastable catalysts. We want to have stable catalysts. Typically, for reactions that we believe have a lot of potential for application, a 1,000-hour test is what we can handle in our laboratory. If we want to extend the 1,000-hour into 5,000 hours or 10,000 hours, well, that will need to be done typically with a third party that has really the interest to commercialize this technology in partnership with us.
So this next question goes back to this nice work you showed everyone on single metal atom catalysts. If we think about that, some of the classic rules that metal nanoparticles that are active could be 3 to 9 nanometers in size. Are these single metal catalysts, are they really leading to a new class of materials that are just completely different from our traditional thinking?
Yeah, you see, indeed, they are different. They are different in a sense that their electronic structure is highly tunable, and the electronic structure is highly tunable through the interaction with the carrier. That's first. So the carrier in single atom catalysis is way more important than the carrier in a classical nanoparticulate system. So the interaction with the carrier is very important, but also the fact that we can also tune the coordination of this single atom. So we can have different ligands on that single atom besides the carrier elements that could further change the electronic properties. And that's why these materials resemble more a homogeneous system that is surrounded by ligands that are altering the electronic properties of the metal center than a classical nanoparticle. Having said that, a single atom catalyst, a heterogeneous catalyst, is not the ultimate miracle that can be used for any reaction. So reactions that require very strong metallic character, like for example hydrogenations, would be much more efficiently run on a nanoparticle, a tiny nanoparticle though, doesn't need to be a big nanoparticle, compared to a single atom. So again, the optimal geometry and the optimal structure of the catalyst is given by the reaction demands. So, and that's why I notice sometimes in the literature a big tendency of people to believe that single atoms are miracles. No, single atoms could be extremely efficient if cationic species are required in the catalytic cycle.
The next question, in the first part of your presentation, you presented the Lindlar catalyst. What tools did you use to find that trimeric ensemble? Was it modeling, reactions, adsorption?
Yes. Yeah, so this was mostly driven by density functional theory, but we also conducted in order to have an estimate that the size is trimeric, was done by volumetric adsorption studies in order with different probe molecules, trying to see the molecular size with respect to and induce from that the size of the ensembles.
The next question is about your preparation of the single metal atom catalyst. What techniques are available for dispersing this material, dispersing the single metal atoms on the catalyst supports?
They are really a plethora of techniques, but all the techniques that I have presented here, except for one of the examples in the CO2 hydrogenation case study, make use of dry impregnation. So this is a simple dry impregnation with no precaution as you would do a dry impregnation of a standard nanoparticle. The only aspect that you have to keep in mind, and this is pretty logical to avoid or minimize metal agglomeration, is to have diluted metal solutions. So no sophisticated methods are used here to produce a stable single atom catalyst. They are extreme with very well controlled, grafting of ligands that are decomposed in a controlled manner. There are methods where you do copolymerization of the host in the presence of the metal site that is basically embedded in the structure. But what I have shown you here, because we want to produce a scalable catalyst that can be commercialized, is based on impregnation.
Okay. So the next question is on economics. Have you, or do you know of anyone who's published a techno-economic analysis for methane oxychlorination or oxybromination?
No, I do not know about any study that has been published. I only know that there are claims by companies that commercialize this technology for propane to olefins that claim beneficial economics. We have done our own analysis of the economics of methane and ethane and propane, not oxybromination, but oxychlorination, which is the technology that I'm advocating most because of the wider availability of chlorine with respect to bromine. And so if we want to tackle a natural gas problem, we really need to have an oxidant that is widely available. And these numbers cannot be disclosed because they are confidential. I'm sorry.
This is also a question about the oxychlorination. Is there a concern that the HCl could contaminate the olefin produced?
Well, yes, there is a concern, and actually HCl separation in order to recycle it, because in oxychlorination you can keep recycling the HCl upon dehydrochlorination of the alkyl halide or the alkyl chloride, and that's why one of the most critical aspects in this technology is the workup of the olefin stream separation. Yeah. So separation is very critical.
Someone has asked, can you clarify, is Total going to scale up the methanol synthesis from CO2?
Yeah, so Total has publicly, so what I can tell what has been publicly said, Total has publicly stated that they are looking into the demonstration of this technology in a pilot or mini plant facility. This technology, the demonstration of this technology, I think is going to be a reality. But one has to keep in mind that at present, with the cost of the existing cost of green hydrogen, and this was published by us in a recent techno-economical analysis, with the recent cost of green hydrogen, the cost of the resulting methanol, let's call it green methanol, is still prohibitive with respect to fossil methanol. So again, cheap or better materials for producing hydrogen, renewable hydrogen, would be required.
Okay, so this is another follow-up that really is in a similar type of question. Someone has one of the attendees has a concern about high energy requirements for converting CO2. Did you do the similar type of life cycle analysis on that? Has your life cycle analysis shown benefits or opportunities?
I think that the current life cycle analysis shows that really the Achilles heel of CO2 hydrogenation is not so much on the energy side, is not so much on the catalyst cost side. As I said, is on the hydrogen, is on the raw material, actually on the raw material cost, and particularly hydrogen. So the cost of methanol derived from CO2 will carry an 80 to 85% the cost of the hydrogen, the way hydrogen is produced.
Okay. This next question points back to your work with palladium, and the question is, which is the better matrix for palladium, the carbon nitride, excuse me, or carbon, and how does that affect the performance of the palladium?
Yeah, well, that's a good question. I think that I don't have a definitive answer, and therefore a full understanding. In some applications, carbon nitride seems exceptional, and in some other applications, let's say standard carbons or standard nitrogen dope carbons perform better. So I cannot yet rationalize what kind of descriptor makes this difference. But in general, nitrogen dope carbons, if you don't have strong issues with coking, because that's what I said, you know, the nitrogen groups could really foster coke formation, which you can basically eliminate by using the metal that strong, like platinum, that strongly interacts with the standard carbon. Typically, standard carbons are more effective. The beauty of carbon nitride, and that's the reason why we have used carbon nitride so extensively, is that the structure is better defined. So it allows better understanding.
Staying with the palladium and the single atom catalysis, is there a successful commercial implementation of this?
To my knowledge, no press release has been made on this technology yet. No.
Okay. Is there a significant problem with the single metal or single atom catalysis, whether it be fabrication or sintering or some other issue?
Yeah, I think that's the reason why probably they are not yet commercialized, because synthesis-wise they are really very easy to make. I think there is still a lot of conservatism in the fact that people believe in that these metals are going to sinter or they are going to leach. The case study that we conducted on the Suzuki coupling that I have shown, this was done together with a medicinal chemistry company in Switzerland, and this benchmark test and the turnover frequencies have been benchmarked by a medicinal chemistry company, and the stability as well. So it permeated as an academic study, but it has been heavily conducted on commercial basis. And so I do believe that the skepticism with the single atom heterogeneous catalyst derive from the fact that people think that you need very difficult routes to make them and that they are not stable. And regarding the cost of the routes, I basically debate that, and I don't think this is the case, as I have pointed out. Regarding the stability, well, it very much depends on the application, but this can be tuned, and that's, I think, the ability that we have with the versatility of these systems. Indeed, the stability is not only thermal stability. If we're talking about liquid phase applications, regarding replacement of homogeneous catalyst, for example, one key aspect is the resistance of the single atom towards certain solvents or towards certain reagents that could basically extract into the solution the single atom. But that can be moderated either by moving into a different solvent or by, again, enhancing the interaction of the single atom with the host. And as I have shown, it's possible to modify that very significantly.
So the next question gets back to economics, and someone is asking, looking at the current increase in price of palladium, are you now thinking about investigating lower cost metals for some of these applications?
Yeah, thank you for this question. Indeed, so this is work under preparation and prior to having it published, but essentially we are mostly working now with single atoms of iron, single atoms of cobalt, single atoms of copper, single atoms of nickel in a wide range of applications, and that go from homogeneous type mimics for fine chemical applications towards electrochemical applications for small molecule activation. This is very well possible to synthesize, and so I agree that the next step in single atom catalysis is to demonstrate abundant metals. Yes, we are doing that.
So, Javier, this is going to be the last question for today. We're running out of time. We still have many more questions, and I apologize that we won't be able to get to all of them this morning, but we'll try to get back to everyone and answer them. So the last question for today's session points back to your discussion on palladium and indium oxide. Is it only the active phase in that palladium indium oxide that drives the methanol selectivity, or how does the support play any role?
The support plays a very strong role, but I didn't talk about support effects. Actually, the support of this catalyst is zirconia. So indium, but I did not show that. I showed the bulk indium oxide system promoted by palladium. The real catalytic material requires having zirconia as a carrier for indium oxide, and then on top of that you put palladium. And the role of zirconia is very important because zirconia has actually two effects. On the one hand, if you choose the right polymorph of zirconia, which in our hands is always the monoclinic phase, it first increases heavily the uptake of CO2. So it basically co-catalyzes the adsorption of CO2 in the neighborhood of the interface with the indium oxide phase. And second, it also helps creating vacancies, oxygen vacancies on indium oxide. So zirconia is an extremely important, we call it support, but it's an extremely important ingredient in the catalyst.
Javier, thank you very much for the wonderful presentation today. Is there anything else you'd like to mention before we close out the session?
Well, I like to say again, thank you very much for giving me the opportunity. Thank you for those that participated, and thank you very much for the very nice questions. I hope they were at least partially answered. And if the word partial still exists, you guys know my email, and I would be very happy to elaborate on further questions. Thank you so much.
Great. Thank you everyone for participating in today's webinar. We hope you found it useful and beneficial. Do not forget to check back for upcoming webinars on micromeritics.com/webinars, and hope to welcome you again very soon. Thank you and have a good day.